Yes, but we can hear Dr. Benowitz.
Okay, good. So the first problem is P1 was growing on fat minus GAP plus PAP minus and was used to transduce a fat plus GAP minus PAP plus strain, and selection was for GAP plus transductance. And here are the recombinant classes, and I'll tell you about my highlighting in a moment. So the question is, what is the gene order? And you use a diagram. Okay, so let me join. So if the order is GAP plus, FAP minus, FAT minus, that is the donor. You always have to pay attention to the symbols here in this class, right? So minus, plus, minus here. So because that is what the donor is providing, right? So if you have this order, GAP plus, PAP B minus, FAT minus, then you have the multiple crossovers here. So you have this one. So you have GAP plus, and then you pick this marker, PAP plus, you cross over again here, you pick FAT minus, and you will get a recombinant. Let me increase that here. So you get a recombinant that is GAP plus, PAP plus, FAT minus, and that corresponds to the rarest class of recombinants. Okay? This is the rarest class. So here, this is the rarest class of recombinants. If I had put the order GAP plus, FAT minus, PAP minus, you would have seen that you do not obtain that recombinant. Is that clear, or you want me to do the other one?
Yeah, Dr. Benuet, this is Mike. I was reviewing the notes, and it was mentioning something about that there's 3 situations in which we have 2 crossover events and only 1 situation in which we have 4. Can you clarify that a little as to why we used 4 here?
Oh, because the rarest class of recombinants, this one, is the one that it gives you the hint as to what the order is. And the rarest class of recombinants is obtained if you have 4 different crossovers. That's why it's rare, because having 4 different crossovers in this interval is a very rare event.
That makes way more sense. Okay.
Okay. So the other ones, the double crossovers, the ones that have only 2 crossovers, represent these all 3 classes here. Okay. And I can demonstrate that to you. So if you were to have a crossover only, let me do a different color. Let's say you had GAP plus, and then you have this crossover here, you will get GAP plus, PAP plus, FAT plus, and then we look here, and you see that that represents this class here.
Okay, I get it, definitely. That makes way more sense. Okay.
Okay. And now if you were to do, let me erase that. So if I were to do another one, let's say we go this way, and then we cross over here, we will get GAP plus, PAP minus, FAT plus. So PAP minus is the one. So PAP minus, so you will get this class here. Okay? This one. Okay. And and then the other possibility is if we have this one here, So we'll get GAP plus, PAP minus, FAD minus, and that is this class here. Okay? So the double crossovers are usually more abundant than the quadruple crossovers. This is a little different than when one is doing Mendelian genetics and recombination frequency, as we did with phages, because the closer the markers are here, the higher the co-transduction frequency, the farther apart they are, the lower it is. So it's kind of backwards. I know this is what it can be confusing. So, okay, so the next question is, what is the co-transduction frequency between GAP and FAD? Okay, so the first thing we have to look is at the donor. So we have to, let me erase this here. So GAP plus, so and FAD, so it came with FAD minus, not with FAD plus, it came with this. So you have to look in these recombinant classes which ones have FAD minus, and there are these two, okay? So that is independent of PAP. We are only looking at co-transduction between any two markers at a time now. Okay, so if we add these numbers, so the total number of progeny is 180, okay? And if we add 54 and 9, let me go here to this thing. Okay. So if we have the, first of all, co-transduction frequency is the number of recombinants divided by total progeny. The recombinants that you're looking at, in this case, is GAP and FAD, but the symbol makes a difference. So, so you have 54 plus 9, 63 divided by 180 gives you 0.35. So frequency is always less than 1. If you multiply that by 100, you get the percent co-transduction. So they are 35% co-transducible, these two markers. Okay, are there any questions about that?
No, that makes sense.
Okay, so now we are asking, what is the co-transduction frequency between GAP and PAB? Okay, again, we go and look here, okay, and it's PAB minus that came with GAP plus. So there are these two classes, okay, so we add 54 and 19 are the recombinants that we are interested in now. Okay, so 54 and 19 is 73 divided by 180 equals 0.4055 times 100 equals 40.5 or 0.6% co-transduction. You can round up this. And then I said, draw a map showing the localization of the marker. So we determined that GAP and PAB are 40.5% co-transducible, and that these two markers, GAP and FAD, are 35% co-transducible. That was the first one here, right? 35 and 40.5. Is that clear? Are there any questions about this?
Can you scroll down again to part D, Professor?
Oh, yes. Sorry.
Thank you.
Okay, so this problems basically have the same moves. I mean, there are other situations that are a little more complex, and I'm avoiding them. I'm trying to make the situation simpler. Okay, this is not an advanced course in genetics. This is just learning the basics of genetics in microorganisms. But this is a common way of refining mapping Okay, so can I move to the next one or?
Yes.
Okay. So P1 was grown on a cis plus, peer plus, trip plus strain, and it was used to transduce a cis minus, peer minus, trip minus strain. And the transductants were selected on medium containing uracil, so you're selecting peer plus and tryptophan. So here are some results. So, okay, I eliminated the table that follows this because that was, really involved in terms of figuring out from the media. It was not straightforward. Again, I'm trying to simplify things. So here, these are just questions that I wanted you to answer. So you add 10 to the 8th phage. So here you're only. So there are no cells. You plate this and you get 0 colonies. And then the question is, why are there no colonies here? Somebody tell me.
Because this is Mike, we don't have any cells for the phages to actually transduce.
Correct. Very good. Excellent. Excellent. So this is just a control, to make sure that your phage lysate is not contaminated with cells. Okay? Because if something had grown here, you better worry and go back to your lysate. And it happens, so that's why this is important control. Now you have cells only control, no phage, and you have 4 colonies that you get. What are these colonies? So the question is, what is the likely origin of the 4 colonies when only cells were plated? Remember, you are plating these cells, cis minus, peer minus, trip minus.
This is Mike again.
And you are selected for, yeah, so you're selecting uracil, right?
Yeah, so I would think that they're just like genetic mutants in the colonies that would be able to use the uracil and they can grow without being transduced.
Okay, but there is the medium has no uracil and no tryptophan. And they are cis minus and trip minus. What do you think they are? You said something at the beginning that was kind of in the right direction.
Could it be like contamination from your lysate?
No, because there is no phage here.
Oh, that's right. Okay.
These are only the recipient cells that you have tested on the different media. You test and make, they require cis, they require peer, they require trip. But now you're plating a ton of bacteria. This is not 100. This is, 10 million or 100 million cells that you're plating. And you get 4 colonies. Anybody?
Dr. Benya?
Yes.
This is Joe. I was thinking perhaps your recipients, maybe not all of them were fully transformed.
No, but it's a pure culture. Cis minus, peer minus, trip minus. It has not been transduced. There's no phage. You tested and they were, before you plated, they behaved like this. But now you plate a ton of them and you get 4 colonies.
Oh, I'm kind of thinking now that like as all of the cells that you're plating, since there's so many, as they die, certain cells are able to use the like nucleotides or you know the proteins that were from the dead cells to use them for their own metabolism. No.
That's not a bad. That's not a bad answer. Actually, it's quite interesting. It could happen. Yes, it could happen. I like it that you thought of something, that is, out of the box. Good. So these colonies, what they represent is revertants. Remember that if you plate histidine minus, a lot of histidine minus on a plate that has no histidine, you are going to get some revertants. They are very rare, but remember that you're plating here 10 to the 8 or 10 to the 9 cells. So this, most likely, you will have to demonstrate that, and not what you just said about, cross-feeding, that these are revertants. But it's possible because of the immense number of cells that you're plating. Okay? If you were plating 1,000 or a million, unlikely. But you're plating, at least maybe 10 to the 8, 10 to the 9s here. Okay, so this is another control, to make sure that your markers, you're not getting a ton of these colonies, because that will interfere with your results. And then C, so here is phage and cells. So what are these 200 represent? What do they represent?
Transduced cells?
Yes, those are transductants, because you're mixing both and you're plating and you're getting this many transductants. Okay? So they are peer plus and trip plus transductants. Okay? So this is just to show, the use of controls in a transduction. So C is the real transduction. And of course, here is just you're looking at transductants of one type, and then you test this to make sure that whether they are cis plus or minus. That's the idea here. But here you're just looking at peer plus, trip plus. And obviously in the medium you will have cysteine to allow those that are cis requiring to grow. Okay, any questions about this? Okay, so let's go. This is the last problem in the transduction problem where I'm skipping 3 and I'll tell you why. P1 was grown on a NAD plus, LIP plus, LU S minus strain, and was used to transduce a NAD, this is for nalidixic acid, and LIP minus, that's lipids, and LU S plus strain. And LIP plus transductants were selected. Okay, and here are the classes that you have, and then the total number is 298. And then the question is, what is the gene order? And you describe with diagrams. So you have to do it by trial and error. I didn't do both. I just put one that is the order. So if you have, let me increase this. So if you have, let me see if I can, maybe so if you have 4 crossovers, and I write them in this order, you will have LIP plus, NAD minus, LU minus. Okay? And so the rarest class is LIP plus. All of them are going to be LIP plus because that's what you're selecting for. LU minus, NAD minus. So that indicates that this is the correct gene order. If you had put LU in the middle, you would have seen that you get another genotype, and that will not correspond to the rarest recombinant class. this is the one where you always start. This is the one that gives you the clue. It's like mapping and doing Mendelian genetics. One always looks for the rarest recombinants to determine the gene order. It always gives the clue. Okay, are there any questions about this? Do people want me to do the other one that doesn't give the correct order?
Yes, can you do that as well?
Yes, okay. So if I have, okay, so let me, just do here. So if I have, so lip, oops, let me do it here. Oh, and I wanted to point out too that I said the order is lip, lip, nad, lu, lip, nad, lu, but it's the same as lu, nad, lip. Because you don't know what is next here, to the right and to the left. So it's either one is fine. Okay, so let me create some space here. So if I put lip, writing this is a little cumbersome, and then I put lu, and then nan, okay, I don't have a pen to do this, so I need to do the markers plus, plus, and minus for lu. Okay, so this is minus, this is plus, and this is plus. Okay, and then here we have lip minus, lu plus, and not minus. Okay, so if we have 4 crossovers, so if we have a crossover here, a crossover here, a crossover here, and a crossover here. And note that the crossovers are not written over the genes. That's incorrect. Anybody that does that gets points off. So if we have this situation, then we will have, lip plus, lu plus, not plus. So all of them will be plus. And we look here, and we see that the rarest class is actually has 2, nad and lu are minus. The class that I just drawn is actually there, but it's obtained, this one is obtained 32 by double crossovers. So that or immediately tells you that this order that I just drew, this is absolutely wrong. Any questions about that? Okay, and the other thing is that, again, like in the previous one, if you have double crossover only, let's say you will get lip plus, nad minus, lu plus. So it will be one of these classes. So nad minus, lu plus, it will be this one, the most abundant class. And if you have this one here, you will get lib plus, nat plus, lu plus, which is this class here. All of them are plus. And if you get this double crossover here, you get lib plus, nat plus, lu minus. So nat plus, lu minus, okay, this class here. So that's, so you know where the different recombinant classes come, and they represent double crossovers. Okay, so now what is the co-transduction frequency between lib and nat? So again, we have to go back to the donor. So it is nat plus. So you look here at the recombinants that have nat plus, there are 94 and 32. So 94 plus 32 equals 126 divided by 298 is 0.4228 times 100 gives 42.28 or 42.3 co-transduction frequency, or a percent co-transduction. Okay? Any questions about that? Okay, and then the next one is, what is the co-transduction frequency between lib and lu? Again, we go and it's lu minus. So I should put the yellow here. So I look at this lu minuses, they are 94 plus 2. So 94 plus 2, 96 divided by 298 equals 0.3221 times 100 equals 32.2% co-transduction, or the markers are 32%, 0.2 co-transducible. Okay, and now you have a map. So remember the order was lib, nat, lu, and the co-transduction frequency between these first two markers is 42.3%, and between lib and lu is 32.2%. So the farther away, the less co-transduction. Okay, is that clear?
Yes.
Yes.
Okay, so I'm now going to do the problem 3, and because I was working on these problems yesterday, and that problem has an error. Again, this is a problem taken from a book. This one in general, I make up my own problems, because then, I tried to do it quickly, I copied it, and then as I was doing it, I should have done the problem before I posted it, and it's incorrect. So I will skip. I will make sure that anything that I put in the quiz is something that I have tested before, okay, and done it and made sure and confirm. So